The lesson topic for this video is solving exponential equations using logs. So here are the steps we're going to follow, and we'll do some examples on the next couple of slides. To solve an exponential function for x, we need to first isolate the base and the exponent. Isolate means get it alone, so we need to get the base and the exponent alone. So that might be, for example, like 3x needs to be alone on one side of the equal sign. Then we need to change it to a log. So we're going to convert whatever we have as an exponential equation to a log. Then we're going to evaluate using the change of base formula or the log button if you have the common log. And then if necessary at the end we need to get x alone so it is fully solved for x. Let's try some. Alright, so the first example says 3 to the x power equals 21. The first step on the previous screen was isolate the base and the exponent. Notice in this situation, we already have the base and the exponent isolated, and it equals 21. So that's done. And you'll probably notice that we've done something like this in previous lessons already. They're going to get a little bit more complex in a couple of examples. All right, so we're going to then change it to a log. So we're going to change this to log. Base is, again, the base is 3 here, of 21 equals the exponent, which is x. Log base 3 of 21 equals x. In order to solve for x, we need to use the change of base formula since the base is 3. So we're going to say log of 21 over log of 3 is equal to x. Now we're in the common log because there's a 10 here. It doesn't show up, but that is a common log. And we can do the math on our calculator and to find out the value of x. So 2.771 is the value of x. And like I mentioned in other lessons, we can put this value in for x here to make sure that it's true in the end. All right, the second example, go ahead and do this one on your own, this middle one here, and then we're going to talk about how the third one is different. Go ahead and do that one, and I will show the correct answer in just a second. Okay, so you see the work I've shown there and our solution for x equals 4.615. Again, I keep stressing this, but it's important that if you want to double check that you are correct, we can always put our value for x into our equation to make sure it's true. All right, now the next one is just a little bit different. Notice that this one says 5 raised to the 3x power equals 90. We have still got our step 1 completed, and that is to isolate the base and the exponent. That is alone on one side of the equal sign. So next we are going to change this to a log. We're going to write log base 5 of 90 equals 3x. Notice our log is still equal to our exponent, which is 3x. All right, now can we do this on our calculator right now? No, we can't, so we're going to need to use the change of base formula again. So log of 90, the common log of 90, over the common log of 5 equals 3x. Now don't worry about this 3x yet. We're just going to keep simplifying. So now log of 90 over log of 5 is 2.796. And that equals 3x. Now notice that very last step on your notes, if you wrote down the steps, which I hope you did on the previous screen, we need to finally, at the very end, get x alone. Because right now we have 3x equals this, and we need to find out what x equals. So at this point, we can divide both sides by 3, and we can solve for x. 0.932. All right, so what you'll see on these two examples is something a little bit more complex. Now remember back to the first direction in the first slide. Step 1 is to isolate the base and the exponent. So our base is 6 and our exponent is x. We need to isolate that, which means we need to get rid of this cube root. Well, how do we get rid of a cube root? We use the inverse operation, which is to raise it to the 3rd power, or cube it. We need to therefore cube both sides of our equation. The cube root and the cube are going to cancel out on that side. And then we're going to be left with 6 raised to the, 6 raised to the x power equals 729,000. All right, so now we have isolated our base and our exponent, and so now we're going to change it to a log. So log base 6 of 729,000 is equal to the exponent, which is x. All right, since this is a log with base 6, we need to use the change of base formula, so we're going to write log of 729,000 over log of 6. All right, go ahead and calculate that. And we get x equals 7.534. One last example, and again, something a little bit different happens here. We do not have our base and our exponent isolated. But what some people do incorrectly on this example is they want to multiply the 2.5 and the 1.5 right away and change it to, let's see, 3.75. Do not do that. We cannot multiply these first because based on the order of operations, we would first need to raise this to the x power before multiplying it by 2.5. So the thing you cannot do right now is multiply these two values. What we need to do is we need to isolate the 1.5 that's raised to the x power, which means we need to undo what's being done out here, which is multiplying by 2.5. Okay? We're multiplying this whole thing by 2.5. So we have to divide by 2.5. That's the inverse operation there. So divide by 2.5 on both sides. The 2.5s will cancel over here. We're going to have 1.5 raised to the x power equals 6.16. All right, now we've got a base and an exponent isolated. Here's our base of 1.5 and our exponent, and we can change this to a log. So log base is 1.5 of 6.16 is equal to our exponent, which is x. Change of base formula. Hopefully you're getting used to doing that. And then we compute our value for x. And there we go. And again, if we wanted to plug that value in for our exponent up here, make sure it's true, that would be a great strategy to checking your work and especially true for a test. So that's all for now.